Hello student, today we are going to discuss about a sufficient condition of a Laplace transform and some more properties of a Laplace transform, like change of a scale property, how we find the Laplace transform if we multiply by integral power of a t in a function ft or divide by the integral power of a t in a function ft. So, let us discuss about a sufficient condition of a Laplace transform. So, what is the sufficient condition? If ft be any function, then if the function belongs to a class A, means if function is a class A function, then Laplace transform must be exist. So, what is the sufficient condition? If ft is function of class A, function of a class A. So, this one is a what? This one is a sufficient condition. Although, if function is not belongs in a class A function, class A category, then also there is a chance we may able to find out a Laplace transform, because this one is a sufficient condition. But if function is from the category of a class A function, then surely we able to find out a Laplace transform. So, this one is a sufficient condition of a Laplace transform. Now, question is what is a class A function? Class A function. Which function we say class A function? So, let us define the class A function. So, a function ft, a function ft is said to be class A function if function ft is of exponential order and ft is continuous or piecewise continuous for all t greater than 0, So, such type of a function is said to be a class A function, means function is either continuous from 0 to infinite or piecewise continuous from 0 to infinite, and nature of a function means a function is of a exponential order. So, now one another term is here, how we know that the function have a exponential order? Because already we studied the how we know that the function is continuous or piecewise continuous, but up to this level we doesn't know about how we know that the function is of a exponential order. So, one thing again we clear here, if function is a class A function, then it must be necessary, because this one is a sufficient condition, it must be necessary the Laplace transform must be exist. But what is a class A function? A function is said to be a class A function if function have exponential order and function is either continuous or piecewise continuous for all t greater than 0. So, Now question is what is the exponential order? How we check that a function have exponential order or not? So a function ft is said to have exponential order. A function ft is said to have exponential order if there exists a constant m and a real number sigma such that mod of a ft is less than m into e to power sigma t. So a function ft is said to have an exponential order if there exists a constant m and a real number sigma such that mod of a ft is less than m into e to power sigma t for all t greater than t0. So in other word means how we write here, we able to write limit t tends to infinite ft into e to power minus sigma t tends to what? Tends to 0. Then we say that function ft have a exponential order, or we may also write this one, limit t tends to infinite ft upon e to power sigma t tends to what? Tends to 0. Then we say that ft have a exponential order, and what is the order of a what is the means exponential order of a function ft? Sigma is a what? Sigma is a order of a exponential order of a function ft. So there is a need to check this limit for any function ft. If this limit tends to 0, then we say that ft have a exponential order, otherwise ft does not have a exponential order. So what is the sufficient condition for the existence of a Laplace transform? The function must be a class A function. And which function we say? Class A function? A function ft is said to be a class A function if it's have a exponential order and ft is a continuous or piecewise continuous from t equals 0 to infinite. And what is the exponential order? Which function have exponential order? A function ft is said to have a exponential order if there exists a constant m and a real number sigma such that mod of ft is less than m into e to power sigma t for all t greater than t0. And here we may write this expression like this one, limit t tends to infinite ft into e to power sigma t tends to 0, or limit t tends to infinite ft upon e to power sigma t. Now question is means how we identify any function ft have exponential order or not. So here we try to solve some numerical example, means to identify the given function is of exponential order or not. So here we write two function. First one is ft equal t square and second one is ft equal e to power t square. So what is the solution? How we identify? As we say that we try to find out the limit t tends to infinite ft into e to power sigma t. So here what is the ft in a first question? Ft is the what? Here ft equal in a first question ft equal t square. Ft equal t square. Now limit t tends to infinite. T tends to infinite ft upon e to power something here a real number into t. If be able to find out a real number here sigma in a such a way the denominator is too much large in comparison of a numerator. If we able to find, once again I repeat this statement, if we able to find out here a real number in such a way the denominator become larger, too much larger in comparison of a numerator, then we say that ft have a exponential order. So in this case suppose here we assume that sigma be any constant or we try to find out the limit. So here this one is a limit t tends to infinite t square, limit t tends to infinite, here we write a sigma t, ft is a t square upon e to power sigma t, Now here t tends to infinite by infinite, so we apply the L'Hospital rule. So this become what? Limit t tends to infinite 2t, differentiate numerator and denominator, sigma e to power sigma t with respect to t. Now again this one in a indeterminate form, infinite by infinite. So again we apply what? Again we apply the L'Hospital rule. Again we differentiate numerator and denominator with respect to t. Then if we differentiate numerator, then this become 2. And if we differentiate the denominator, this becomes sigma square into e to power sigma t. So now we able to find out the limit. So what is the limit here? 2 upon sigma into e to power sigma t. If t tends to infinite, then this term tends to infinite because e to power infinite with the infinite. So for any value of a sigma greater than 0, so here 2 upon sigma square into infinite, so this become what? This become 0. So this function have a exponential order. So this function have a exponential order. Provided what? Provided sigma is greater than 0. So for any value of a sigma greater than 0, this function ft equal t square have a exponential order. Now we try to examine the second function ft equal e to power t square is of exponential order or not. So ft equal, second one is a ft equal e to power t square, t square. So, now how we know that this function have exponential order or not? We try to find out the limit. Limit t tends to infinite ft upon e to power sigma t. Now, this one equal limit t tends to infinite ft with the e to power t square upon e to power sigma t. Now, this become limit t tends to infinite e to power t square into e to power minus sigma t. This become limit t tends to infinite e to power t into 1 t minus sigma, and the limit of this one equal to what? Limit of this one equal infinite means this one does not equal to 0. This means this one is a, this function have a not a, this function is a not of a exponential order. So, not an exponential order, not here we write, not here we write, here we write. Thus, we conclude that function ft equal e to power t square does not have exponential order, does not have an exponential order, exponential order. So, from here also we able to identify this function, means this function have ft have exponential order or not, because here we unable to find out any real number, which give the denominator is larger than the numerator. If we put a sigma equal 1 e to power t, obviously e to power t is less than e to power t square. If we put e to power 3, sigma is a 3, e to power 3 t is less than e to power t square. So, we unable to find out such value of a sigma by which the denominator is too much large in comparison of a numerator, or denominator is larger in comparison of a numerator. So, from here also we able to decide e to power t square is not have an exponential order. So, in this way we able to decide either the function have exponential order or not. If the function have exponential order, then surely we able to find out the Laplace transform of that function, because this one is a sufficient condition for the existence of a Laplace transform. Once again I repeat the statement, means this one is a sufficient condition, this one is a not necessary condition. It not necessary, if this condition is not true, we unable to find out a Laplace transform. Maybe we able to find out a, or maybe there exists a Laplace transform of that function if the function doesn't have a exponential order. But if the function have exponential order and function is a piecewise or continuous for t equal to 0 to infinite, then surely function Laplace transform of that function must be exist. So, this one is a what? Existence theorem. Now,